which is the official last week of class, and the week to follow. And the week following that is actually finals week. Does anyone have a final exam? Yeah.
Tuesday.
On Tuesday, yeah. But anyway, what time is it?
The professor doesn't know.
Okay, well, you'll let me know, and I'll find out what room's available, and we'll have a couple of lectures in May. Alrighty. So last time we were talking about something we studied last semester, the phenomenon of coherent population trapping, which is seen when we have a kind of lambda system where we have two states that we'll call ground states, metastable states, and some excited state, and we can drive the system with a laser that couples state G sub A to the excited state with some Rabi frequency, and similarly there's some coupling between the state G sub B and the excited state. And what we have in this case is that if this system spontaneously decays through, say, two channels, that the steady state is that the system is pumped into a dark state. A state that is uncoupled from the Hamiltonian that describes the atom-laser interaction. And so there is no matrix element between this state and the excited state. And thus, if the atom ends up in that state, it will forever stay in that state. But moreover, if we just solve the master equation without thinking about quantum trajectories, then we find that where the dark state is a weighted sum or superposition of the two ground states. And the phenomenon of coherent population trapping was observed in, some laser spectroscopy experiments. I don't know exactly when, probably in the 1970s, I would guess. So what we're wanting to do is to study this from the point of view of quantum trajectories, and we talked about that last time, but I want to just maybe talk about it more concretely in a specific example. So I want to look at the problem of where we have this kind of CPT, we're in population trapping with Zeeman degeneracy. So in particular, we're looking at an atom where we have a multiplet of magnetic sublevels or Zeeman sublevels associated with the total angular momentum, which we'll generically call J. Okay? It could be called F if we were precise, if we wanted to include the nuclear spin and all that, but I'm just generically calling it J. So there's some ground manifold that has a total angular momentum J equals 1. And if J equals 1, there are 3, also known as 2 times J plus 1, the levels with the magnetic quantum numbers +1, -1, and 0. And similarly, we'll have some excited state which we'll also take to have J equals 1, where we have the same magnetic quantum numbers for the M sub e's, okay? And we'll take this to be an L equals equals 0, say an S state, and this to be an L equals 1 P state. So there's a dipole allowed transition between these states. What we discussed briefly last time is that when we put on a laser on this atom, and let's take the laser to be polarized, okay? It's the laser frequency. This is the laser polarization. That the transitions between the different magnetic sublevels that are driven by the laser depend on the polarization, okay? And that's because the polarization of the photon determines the angular momentum of the photon. It's the total angular momentum in the dipole approximation, because the orbital angular momentum doesn't contribute, okay? And so what we have is a quantization axis, and when we write down these magnetic sublevels, those magnetic sublevels, say for example, that have these quantum numbers, represent, okay, this is saying something about the orbital, for example, that it's a 6s1/2 for cesium or whatever. And then this is the total momentum, maybe this is, F equals 1 or J equals 1. But when we talk about M, we're talking about the projection of angular momentum of the spin, the projection of angular momentum of the atom along some direction, okay? So this is the, for example, JZ quantum number. Whatever Z in this problem, if I don't have anything else that breaks the degeneracy Z, what we call the Z axis is completely up to us, okay? So this Z direction is typically called the quantization axis. All right, so I might, just to emphasize that, I'll put a Z here to emphasize that this is the projection of the atom's angular momentum along the Z-axis, okay? Now, we have some axis I'm calling the Z-axis, which can be whatever direction in space I like. That might be convenient for me. And then I break up the polarization into 3 components. There's a component along the Z-axis that's called pi polarization. And we have components that we call E plus and E minus, which are, well, I have to put my pen down to say that's the left-hand order, see? So you never do it the other way around. This is like that. Those poor lefties. So E sub pi, so this is called sigma plus and this is called sigma minus. And this is the so-called spherical basis. So I have E sub q, where q is 0 plus or minus 1, where E0 is the Z-axis, and E plus or minus 1 are circular polarization relative to the Z-axis. And there's a usual convention here, which I won't get into how we would ever do such a thing, but we do. Okay? So this is really just saying that there's some amount of, if the electric field is oscillating along the direction of the Z-axis, then there is no projection of angular momentum along the z-axis. The photon has one unit of angular momentum, it just has no angular momentum along the z-axis. All of its angular momentum is along the other directions. If the polarization is rotating either, this way or this way relative to the z-axis, then the photon has either +1 or -1 projection, that's in units of h bar, along the direction of the quantization axis. This is not necessarily the direction of propagation of a plane wave. It could be. We could choose the z-axis to be that, but we don't have to, okay?
So what about orbital angular momentum? We just assume it worked at 0?
No, it's there, but it just doesn't contribute. It's in the multipole expansion. It doesn't contribute to the dipole. It would contribute to the quadrupole. That's why you can drive you say, how do you drive an S to D distribution when L changes by 2, right? You go from L equals 0 to L equals 2. How the hell does that happen? You always thought the photon has one unit of angular momentum, but it has orbital as well as spin, so that's how it works. But in a dipole, the orbital doesn't contribute.
Okay.
Yeah. Alrighty. So, what we discussed last time is, according to the addition of angular momentum and the Wigner-Eckert theorem, that we can drive a dipole allowed transition, electric dipole, not a magnetic dipole. If we do that, then ME can be mg plus q, where q can be 0, +1, or -1. You can't change it by one, but you can, and if you change it by 0, that happens only when the polarization is pi, and if it's sigma plus or sigma minus, then I can change that by this amount. So what that means, and the Rabi frequency that goes between these two states depends on the dipole matrix element, right? And I can write that as d dot e laser times e0 minus I dot dot dot. And this matrix element depends on the Wigner-Eckert theorem, okay? So what we find is that this is equal to something I'll call omega naught times a Clegg-Gordon coefficient that is associated with the addition of angular momentum, starting with the angular momentum of the atom, adding the angular momentum of the photon, and ending with the angular momentum in the excited state, okay? So the strength of this transition, that is to say the Rabi frequency, depends on the Clegg-Gordon coefficient, okay? Moreover, the rate of decay, starts in some excited state and goes to the ground state, is gamma times the square of the Clegg-Gordon coefficient, because it depends on the dipole matrix element squared. Okay, and of course it's only this is non-zero only if ME is equal to mg plus q, according to the rules of the addition of angular momentum and Clebsch-Gorn coefficients, which is where the selection rules come from in the first place. Okay. Okay, so for this system, we can appeal to our favorite source to find what the Clebsch-Gorn coefficients are, and they are the following. This guy, the Clebsch-Gorn coefficient is 1 over root 2. For this guy, it's minus 1 over root 2. I think. Nope, I got it backwards. This one is minus and this one's plus. Not that it really matters. And then this guy is equal to plus 1 over 2. This guy is minus 1 over root 2. And then we have a similar kind of thing here. This guy is 1 over root 2. This guy is minus 1 over root 2. And this guy is verboten. It's 0. There is no, the Clebsch-Gorn coefficient that connects those two states is 0. Okay? Okay, so in particular, if I start the system the state of the system, say, is, okay, so let me now say the following thing. So let's choose our electric field to be linear polarized, okay? So I'm gonna have linear polarization. And I'm going to have this polarization along the y direction. I take the real part afterwards, okay? So I'm going to take my quantization axis to be the k-axis. So we have light propagating in some direction, and it's linearly polarized. Call that the y-axis. Doesn't really matter if it be the x-axis. Let's just, I'm going to choose my quantization axis along the propagation direction. In that case, my polarization only has a E plus and E minus component, sigma. There's no pi light because the field is transverse and I can't have any polarization along. So if I choose the polarization, if I choose the quantization axis along the propagation direction, then I only have sigma polarization. I could have sigma plus, I could have sigma minus, or both. In this case, I have both because the linear polarization is a superposition of right and left, okay? So, with that said, if at t equals 0, the state of my system is in the ground state with, say, mg equals -1 along the z-axis. Okay? So if I start there, the only thing I can do is couple from the ground state with -1 to the excited state with m equals 0, right? There's nothing else I can do because there is a sigma minus component, but there is no m equals -2 component in this guy. This guy could decay here, or it could decay here, but it can't decay to this. That's verboten. So I don't have to worry about that. That state won't participate at all in the dynamics because there's no way to get to 0. Because if I'm in the excited state with m equals 0, I can decay here, or I can decay here, but I can't decay to m equals 0. So I have this lambda transition that I talked about over there, okay? Where the two driving are driven by sigma plus and sigma minus polarized light, of which there is an equal component thereof, okay? Yes?
Before we start hitting this with dynamics, how do you actually, so you said we define the polarization axis, or the, like.
The quantization axis.
Yeah, the quantization axis based on the laser, but how do you know a priori that you're starting in this state?
Sure. Well, in practice, you would have to break the symmetry in some way, typically with a magnetic field.
Okay.
And then you would have to do optical pumping to prepare the state into that magnetic sublevel. But for the moment, there's just a conceptual, we just imagine,
Sure, okay.
but in a real experiment, we would have to do something to break the symmetry.
Gotcha.
At the moment, we're not gonna break the symmetry, and we're gonna do a conceptual Gedanken experiment.
Sounds good.
Good, all right, so we start here, and I could come back here, I'll drive for this, and I can end up here, and that's all that can happen, right? Okay, so now, I have we have the Rabi frequency that goes between -1 and 0, depends on this Gordon coefficient. So it's -1/√2 omega naught, right? And this guy that connects me between m equals +1 and 0 is +1/√2 omega naught, right? Due to the Gordon coefficients that are written up there. So the dark state in this case is what? Well, it's the thing, so the dark state, we said was this guy. I think I got the sign backwards here. Nope, I got it right. Good. Let's use that over there. So that case is, ground state with m equals -1 minus the ground state weighted by this with +1 divided by the square root of these guys squared. Right? And in this case, this is equal to, because these signs are the same, and I can look, this guy's a minus, and then I have minus that, then it's the symmetric guy. Off to an overall sign, what I have is that the this is the dark state. The symmetric superposition is dark because the amplitudes have opposite signs. The anti-symmetric superposition is bright because of the sign difference. They will have constructive interference. So you can think about the dark state as an interference phenomenon where there are two amplitudes to go to the final excited state, and they destructively interfere if I have this state, and they constructively interfere if I have that state, okay? Of course, 0 is also bright, but because that state would go like that, and that's okay, but we're not starting there. There's nowhere to get there in this particular case. Okay, so, as we discussed last time, now I can ask the question about what would happen if I started in this state and I looked at a quantum trajectory. Well, first of all, I have to ask, what are the jump operators in this case? Well, the jump operators are a little bit more complicated than we had when we had the two-level atom, because we have two possible jumps. I can either emit a sigma plus, or I could emit a sigma minus, right? And the jump operator for emitting sigma plus light is, I can start in the excited state with M excited equals 0, and end in the ground state with M equals -1. I'm sorry. Bleh. L, jump operator. Okay, so that's like our two-level thing. We have an excited and a ground, right? And this would be multiplied by the Clegg-Gordon coefficient associated with that transition. That Clegg-Gordon coefficient in this case is a half. So, you know, it's this over 2. And similarly, for going the other way, I have exactly the same thing. Okay? The sum of this is that is to say, the excited state has a total spontaneous emission rate, gamma, and H effective would just say that I have its imaginary part minus I H bar over 2 times that, right? So that the Hamiltonian H effective is equal to H minus I times the projector onto the excited state. Everyone with me? Questions? Right, that's, the excited state has a finite factor. Yeah.
We're assuming that we measure the polarization of the photon that comes out, right?
These jump operators are the jump operators that correspond to these jump processes.
Okay, so, we know the jump process.
So, but I think this is a very important point, so let me emphasize this. These correspond in the measurement model to an observation on the environment, which is, in this case, the environment is the spontaneously emitted photon. So what measurement would I have had to do in order to determine whether this jump happened or that jump happened? I'd have to measure the polarization, right? So this corresponds to a situation before we just said, oh, here's the atom, and the atom spontaneously emits, and we had the 4 pi steradian of detectors, and we didn't care what the polarization of the light was. We just said there's either a photon or not a photon. But here we're asking, if there is a photon, are you pi, are you sigma plus, or sigma minus? So we have to have some kind of, polarization analyzer. We'd have to have 3 ports, really. But in this case, maybe we only have 2, where we have some quarter wave plates. You see, I know what that means. And, we would have whether, it was sigma plus or sigma minus would correspond to the measurement that corresponds to the measurement record that would tell us did I decay this way or did I decay that way. So by not only collecting whether there is a photon or not, but collecting the polarization of the photon through a particular polarization analyzer, we would have additional information. Very important point.
We still have this exotic 4 pi
I mean, we live in Gedanken land. Okay. Now, we could try to make this work by putting this in a very high finesse cavity to use the Purcell effect to enhance the fact that it would emit into the cavity mode rather than the other part of the 4 pi steradians, and that's the kind of thing one would do if one wanted to actually do these kinds of dynamics in a conditional way. Yeah.
So your analyzer needs to measure all 4 stokes, right? Because
You need to be able to measure, you have the detectors over in all directions,
Yeah.
not just the photon emitted in one direction. This is any old way that it can
that's
go
what's it.
relative to the dipole pattern.
But all 4 stokes in the
Yes.
whole hemisphere. Okay.
Yep. Well, I mean, if you're talking about the Stokes, you might be talking about the Poincare sphere. What that really means is I'm really determining, are you pi, are you sigma plus, or are you sigma
Yeah.
minus? Those are the 3 things I need to know.
Yes.
So I need to analyze this, the photon, not relative to the Poincare sphere, which says I have a fixed direction of propagation, I have an effective qubit. I'm asking the photon, are you sigma plus or sigma minus relative to a fixed direction z,
To the quantum direction.
to the quantization x, not the direction of propagation
Yeah.
of the spontaneous photon. Yes. All right. Good. So that's interesting. So now, we have more than one jump operator, and in this case, if you wanted to do the Monte Carlo simulation, well, you better want to do it if you want to get the final project done. How are you going to determine which jump operator to apply? Because the way we do the Monte Carlo is we first ask, did you emit a photon or not? If you didn't emit a photon, then we evolve according to the non-Hermitian effective Hamiltonian. But if I did jump, then I have to apply the appropriate jump operator. How am I going to determine whether to apply this jump operator or that?
Depends on the calculations.
I would have to calculate the probability.
Yeah.
So the probability of emitting the photon with polarization Q is what? Suppose at some time t, my state is that, and I want to know what is the probability that I see this outcome. Well, the answer to always calculating the probability of a measurement outcome is Born's rule. Born's rule tells us how to calculate the probability of a measurement outcome. But we need to know the probability of, in a little time interval, delta t, of measuring the photon so delta p with polarization q is the Born rule, and the Born rule says I need the POVM element, and the POVM element is n dagger m. Boy, we gotta practice this over and over and over again. This is just something you just have to keep reminding yourself. What's the relationship between the Krauss operator, the POVM? How do I calculate those things? And the POVM element here is related to the Krauss operators, and the Krauss operators are related to jump operators. by the square root of dt. And so this is equal to the expected value of L dagger L dt, or delta t, or small, right? That's what the Monte Carlo tells us. And, okay, so in this case, I have two possible emissions, either Q equals +1 or Q equals -1, and so I would calculate this, would be equal to gamma over 2 delta t times, depending upon whether, with the appropriate m equals plus or minus 1, right? So I would have to just think about L dagger L with that particular state, okay? So I would calculate that I would have to look at the overlap of the state with L plus or minus. Okay. Now in this case, is that probability going to be any different? What is this in this case? Because if you look at this, L dagger L it gets rid of it, right? It doesn't really actually matter in this case. This is going to be equal to gamma over 2 times the probability to be in the excited state at that time. And it's a 50-50 chance. The branching ratio is the same. It doesn't care. So you would just flip a coin with a 50-50 probability, and if it's heads, you go to +1. If it's tails, you go to -1. If there was a different branching ratio, well, then it would matter. But here, it's the same, okay? All right, so we start at time t equals 0. And I want to know, what is the probability to be in the dark state? All right. For a given trajectory. At the initial time, the state is this. The dark state is this. So at the initial time, what is the probability that I'm in the dark state? A half, right? So I start here. I'm driving the system with this laser beam. And for a while, I might be oscillating between this and this, okay? And in that case, what I'll get is, if I didn't have this continuous observation, the system would be in some superposition of just these two states. However, as I am looking at it, for a while, I might not be seeing any photons at all. I won't see any spontaneously emitting photons. In which case, I have to renormalize the system relative to the effective Hamiltonian, okay? And what that's going to do is it's going to take a little bit of population out of this. I'm sorry, it's going to take a little bit of population out of the excited state and move a little bit more to the ground state, because I'm not seeing a photon. But if the state has it doesn't have this equal superposition of bright and dark anymore, because this initial state, what we just said here, the state G mg equals -1, if I look at that, according to what's written over here, that's equal to some superposition of bright, or let's write it this way, which one is which? Dark minus bright over √2. It's an equal superposition of the two. But as I more and more don't see any of these photons as I'm driving the system, there's going to be some population that's growing in the dark state. And the system will start creeping up towards the dark state. Now, I might see a spontaneously emitted photon, and if I see a spontaneously emitted photon, I could see this, and with a 50 chance, or I see that. But this state, the state in the ground state with m equals +1, is also a 50-50 superposition, if I look at that, of the bright and the dark state. So right after I see a photon, whether I see this one or this, boom, I jump back in with a 50% chance probability. And then I start, for example, probably oscillating on this. And for a while I won't see thing, and then boom, I come back, and then maybe eventually, for a long time, because we know in steady state, I eventually get there. And if I average, if I look at the statistical average of many quantum trajectories, then what I'll see on this is something that looks more like that. Okay? And so in this problem, I arrive at the dark state in steady state when I don't see any spontaneous emission. For a long time. And the longer I don't see a spontaneous emission, the more confidence I have that it's in the dark state, because it should have emitted, because it was coupled to the light. And if it's not spontaneously emitting at the rate gamma, it's like, well, it must have been in the dark state. And so you keep putting more of your amplitude into that state. So once again, the no jump up evolution is critical to the dynamics that we see in this quantum trajectory. All right. Now, there's a very important aspect of quantum trajectories that we haven't discussed, and I want to discuss in the general cases, and I want to reapply to this problem. And that's the story of different so-called unravelings of the master equation. What do I mean by this? So when Howard Carmichael first developed this theory in his way and named these things quantum trajectories, he talked about the evolution in terms of a collection of continuous evolution punctuated by jumps as an unraveling. Every quantum trajectory is an unraveling of the history of what's going on conditioned on a measurement record. But what measurement record are we talking about? Because in principle, I could do lots of different measurements. Okay, so we remember, if I have a CP map, we could write that in a multitude of different ways in terms of a set of Krauss operators. The Krauss operators are not unique. There's two sets of Krauss operators written here, the set I'm calling mu and the state I'm calling n sub mu, which are different Krauss operators. That are the same map. Why? Because we remember that the map is associated with the interaction between the system and the ancilla. Here the ancilla is being called the environment, with some unitary interaction between them. And then we look at the environment. Well, if we don't look at the environment, then the evolution of the system alone is this. But we said that this evolution, when we don't look at the environment, is equivalent to having, say, measured the environment with some measurement outcomes mu, and then throwing away the measurement record with the appropriate weighting. So by looking at this red line that I just loosely drew is meant to say, well, I don't have the quantum trajectories, so I have to look at the average over all possible quantum trajectories weighted by the right statistics, and by doing the jump according to the Monte Carlo, we get that, okay? But I could do different measurements, right? And so the MUs, for example, if I do a projective measurement, then I can think about the MUs as the matrix element of the partial matrix element of the system environment unitary for some fiducial state. And the NMUs would then perhaps correspond to a different basis that I might measure in. And if I measure in a different basis, I'm going to get a different measurement record and a different unraveling. So, for the case of, if we look at the, the Lindblad master equation, I just have a differential map. And we wrote this down, say M0 we said was that Krauss operator, and M1 was, say, this Krauss operator, say, for which had one jump operator, where H effective is H minus I over H bar over 2 L dagger L. I can have a different set of jump operators. I can also have a set of jump operators N0 is 1 minus I H effective delta T, and N1 is J square root of delta T, where H effective is H minus I H bar over 2 J dagger J. What relationship do I have to have between the jump operators L and the jump operators J? Well, those are the relationships between the different Krauss operators. So we know that this is the same, that these guys are the same when the NUs are some unitary remixing. It could generally be an isometry, but here I'm talking about it as a unitary remixing of the NUs, right? If this is a unitary matrix, then it's, with a little bit of work, you can easily show that this sum equals this sum. And in this case, what that means is that the J mu's are some unitary remixing of the L mu's. Okay? So I really should write this in terms of more than one jump operator. So, an important lesson here. The Lindblad master equation doesn't uniquely define the jump operators. I can change the jump operators if I change them according, for example, to a unitary matrix. And I will get exactly the same master equation, but with a different set of jump operators. However, the unravelings can be completely different, because the unravelings are conditioned on the measurement record. And the measurement record can be quite different depending upon the measurement I do. Okay, so let me just write that down so you can put it in your notebooks. The Lindblad jump operators are not unique. So I can write the master equation for example, in two different ways. It's the same equation, but with two different sets of jump operators. These represent the same master equation if the J mu's are a unitary remixing of the L mu's. I could use either set of jump operators and I'll get exactly the same solution, okay? You can plug this in for that and show that this equals this, okay? However, the unraveling of the master equation in terms of quantum trajectories is strongly dependent on the jump operators, because they correspond to different information we learn about the system through a measurement of the environment. And depending upon what I look at, I learn something different. How can I reconcile the fact that the master equation doesn't depend on the jump operators, but the quantum trajectories do? Well, yeah,
Ensemble.
because I'm throwing the measurement record away.
It's like ensemble equivalence, right?
Exactly, it's exactly what it is. The fact that there are many different ensembles that represent the same mixed state,
Yeah.
but the different ensembles here correspond to ensembles that are determined by the measurement. But if we throw that measurement record away, then we never had it in the first place, so it didn't really matter what measurement we did. It's that the way we obtain the ensembles, the individual trajectories within the ensemble will be completely different. Okay, let's talk about that in the context of our friend, the this guy, Coherent population tracking, you know, my friend whose name I forgot. It's more than that. Okay. So, let's now make a change. Let's decide that I'm going to decide to analyze the problem by choosing my quantization axis not along K, but along the direction of the polarization. I could do that. So now these are MYs. They're the projection of angular momentum along the y-axis. That's a perfectly good quantization. We typically would call it Z, but what the heck, I'll call it Y, right? So, in this case, my E0 is EY. That's my pi polarization, because I'm choosing my quantization axis. I only have pi, and you know, this guy, I have to do a cyclic permutation. This is Z minus X, XYZ, okay? I could do that, and that would just correspond to, well, okay, so firstly, if I do that, we have to ask ourselves, in this basis now, the only transitions that I drive are these. Now, I want to emphasize an important point here. This state is a different state than the original, because this is the atom which has angular momentum with -1 along the y-axis. It's not the same state. And whatever the physical state is, doesn't matter what our choice of quantization axis is. The physics of what happens is independent of the quantization I choose. However, if I'm doing a measurement, and I do a measurement with respect to, going back to this problem, I said, oh, the photon comes out and I have to have, these things with the wave plates and the detectors and all that stuff. I'm now looking at it relative to the y-axis. So I have a different set of jump operators. The jump operators that, in this case, are, well, what are they? Well, I can emit like this. I can emit like that. I can emit like that. Now, I can never drive the system from here to here because that Gordon coefficient is 0, right? So I can only go, I can Rabi oscillate like this. I can decay here, I can decay here, and I can decay here, right? Question, what's the dark state in this problem? The state G mgy equals 0 is the dark state. Because if I end there, I can't go anywhere. There's only pi light, and that transition is forbidden. But I want to emphasize that this is exactly the same state as before. It's just we have to ask ourselves, what are the eigenvectors of the Jz operator, and what are the eigenvectors of the Jy operator? So what I'm saying is the following. I have Jz has eigenvectors. Yeah, I agree. Yeah, it's a lot better. It's just, I don't really care. It's the angular momentum I care about. Okay? In this case, J equals 1. There are also eigenvectors of the Jy operator. These eigenvectors and these eigenvectors are related to one another. How? Well, they're related by a unitary transformation because any basis in Hilbert space is related by unitary transformation. But in this case, it's a very special one.
Rotation?
It's a rotation in physical space, right? This is a rotation around the x-axis by pi, or minus x, or something like that. Or whatever takes the z-axis to the y-axis. Right, pi over 2. So, I did that, and here's how they're related. And then so I'll come back to our friend, the unraveling. So firstly, 0y, or let's see, m g z equals 0. This is all for j equals 1. Is mg equals, for the z-axis, plus 1, plus mg z equals minus 1 over root 2. Now, did that get erased? No, it did not. Yes. Look what that state is. That state is your father. It's the dark state. The other guys we can write down, mgy equals 1 is equal to iz mg z equals 0 over root 2 plus 1 over root 2, the bright state. Well, I'll write it out. So this you can find by using the Wigner-D matrices, if you know what the hell that means, but it doesn't really matter. Point is, this basis is related to the Z basis through that unitary transformation. This state is the bright state. Okay? So, what does that mean? Well, so we know that this guy is the bright state. I'm sorry, the dark state. If I land in that state, I'm in the dark state. If I'm in one of these guys, well, that guy couples to the laser. And that's clear because, you know, that state couples to the laser as we analyzed in the Z basis. 0 had coupled along Z coupled. And this guy couples. So that's fine. However, the unraveling is quite different. We have a new set of jump operators. The new set of jump operators are the jump operators relative to a different analysis of the photon. In the first case, we're asking, hey, photon, are you oscillating like this, or like this, or like that? And depending upon whether we had this, or this, or this, we learned something about how much angular momentum the atom had relative to that direction. Now we're asking a different question. We're asking the photon, are you oscillating like this, or like that, or like that, right? And that's telling us how much definite projection you have along this axis. As opposed to that, you're either this, or this, or that. You're asking the photon different question, and depending upon what you learn about how much angular momentum was emitted, you learn something about where the atom could be. So let's conclude this lecture by asking ourselves what we expect to see in the quantum trajectory. So far.
Spatial view for the last time.
I know. All right, so at time t equals 0, we're going to start in the same state. Okay? Now, I have to ask myself in that situation, how is that a superposition of the MYs? I have to invert that stuff. And let's see, did I write it down somewhere? And, oh no, I'm starting in mz equals -1, excuse me. That's where I'm starting, that's what we started before, right? mz equals -1. Let's see what the heck that is. That state is equal to 50% in the 0 along y, and which is the dark state. And it's also 50% along a superposition of this guy.
I think it should be minus.
It should be minus. No, this guy,
Out front now.
yeah. This guy, if I add these two together, I get the bright state, which is what I want. Let me get rid of this. This state is a superposition of this. I believe this is correct, Cole. Let's check. So this guy is the dark state. And if I look at the superposition of this plus this, I get the bright state. So as before, when we start in this state, we are in a superposition 50-50 of bright and dark. That state actually has 50% here, and a quarter here, and a quarter here. To start. Okay? So that's my initial state decomposed into this basis. It has 50% in my equals 0, and 50% distributed, a quarter here, a quarter there. And now I turn on the laser. The laser only has this. Okay? So let's do the same drawing. Let's look at the probability to be in the dark state as a function of time. At the initial time, I'm here. Now, I'm Rabi oscillating. I'm not seeing a photon. As before, the no-jump evolution starts creeping me up towards the dark state. But now, suppose I emit a pi photon. What will happen in that case? So I have to calculate, as you will, in your final project, the probability of seeing pi photon, meaning photon that was oscillating along the y direction. That means I emit it like this. What would the post-measurement state be then? Well, it couldn't have been this. If it emitted pi photon, there's no chance in hell that it was there, because this guy can't emit pi. So that gets, and now I have here. So what's the probability in the dark state now? 0. And now I'm not seeing a photon for some period of time, until I see a sigma. I could see a sigma plus or a sigma minus. If it's seeing pi, it will keep going back to this state, but it's never going to have any in my equals 0. And then maybe at some point, boom, I see a sigma emission of a sigma plus, and now I'm stuck. So in this problem, I get to the dark state by an observation of a sigma plus or sigma minus photon relative to y quantization axis. And the average of many of these things over and over and over again will give me the same red curve. Now you can ask yourself which one is going to be, how many, we know that the exact solution is the limit of an infinite number of trajectories, but we never take an infinite number. So it may be the case that one unraveling relative to another is better for finite sampling because they're closer to the smoother curve. In this case, the z quantization axis will give you better error bars than this one. They'll both converge ultimately to the same curve, but each unraveling isn't equally good at getting the error bars right. There's sometimes an optimal unraveling. It's an interesting problem. I want to just, again, re-emphasize the point. The point is that The unravelings correspond to information that I learn about the system that is stored in the environment by measuring the environment. And depending on what I learn, I update the state differently. In this case, seeing the photon convinces me that for sure I was in the dark state, because it's the only way I could have gotten there. There's no other, if I emitted a signal plus or signal minus, I had to have gone from here to here or from there to there. There's no other way. And so boom, I just go there. Whereas in this case, it's kind of more hedging your bets over continuous time. I'm not seeing a photon because there's no emission that takes me relative to the Z analysis of the photon. There's no analysis that convinces me for sure that I'm in the dark state. It only tells me 50%. It's not seeing the photon that convinces me, you know what, I didn't see a photon, it probably was in a dark state. And it just creeps up there over time, longer and longer and longer. Yeah. Yes?
So is there a better unraveling, an unraveling where you can first somehow predict the steady state and then bound the probabilities of jumping into the steady state or out of it?
Yeah, that's a good question, Austin. I don't know if I have. It's not something I've ever studied. You know, it's true that in principle, if I have the master equation, I could try to say, let me solve for the steady state, right? I can just ask for the thing that annihilates the super operator, that's the generator, and I can try to find the steady state. And then I could ask myself, is there an unraveling, what's the right unraveling to choose that gets me there? That's an interesting question.
Bound on the
Yeah,
probabilities.
it's a good question. I don't know the answer. I have to think about it. But I think it's an interesting thing to think about.
I mean, at the very least, I think the error bars are going to be larger in this case because we have these much larger jumps.
That's right.
Yeah, that's what I'm saying. If you can bound these probabilities,
Yeah. Yeah, you can ask your question of, you know, what's the difference going between them. All right, gang. We have one more topic on this that we'll study next when we come back, and we're going to talk about yet other kinds of unravelings that we can do. In particular, you just want to think about the following question. We're looking at a photon coming in, and we're seeing a photon or not, and that's a pretty strong amount of information. Suppose that instead I mix this photon on a beam splitter with a strong local oscillator, so that I do homodyne detection. If I see a photon in here, most of the time it's come from here. I'm not learning that much about the system. And this is a way in which I can see a more weak continuous measure, different kind of trajectories that are related to what's called continuous measurement. I mean, the measurement we're doing is always continuous here. We're always continuously looking at the atom, saying, did you emit, did you emit, did you emit? But every time we see a click, it's like, boom, we do a jump. Whereas here, it's like noise, and it's somehow the integrated effect over a long time that tells me something in that case. So we'll conclude.